everyone. On behalf of INTACH and INTACH Conservation Institutes, I extend a very warm welcome to our speaker, Mr. Geoffrey Wallis, and everyone who has joined us today, today's talk, the Conservation Insights 2020 lecture series. I'm Dr. Padma Rohila, Director, ICI Delhi. A very brief introduction to our speaker, Mr. Geoffrey Wallis, for those who weren't there on the first talk on Monday. Geoffrey Wallis started as an apprentice at Rolls-Royce Aero Engines in Bristol and was involved in restoring the world's oldest beam engine, still working on its original site in England. At the age of 25, he abandoned the aircraft industry and joined Dorothea Restoration, a small company offering a new field of work, restoration engineering, and carrying out repairs to historic machinery, traditional wind and water mills, and architectural metalwork. He served there while the company prospered. He served there as a director for over 30 years and later as their managing director. The company carried out major works on various sites throughout UK and abroad, including the famous House of Parliament, Brunel's Clifton Suspension Bridge in Bristol, and many railway stations, country houses, bridges, plant houses, and historic machinery in Science Museum, London. After his retirement in 2007, he's working as a consultant. His recent projects in London include the Tower Bridge and the Theatre Royal. He has also worked on many sites for both historic England and the National Trust in UK, with overseas project at Armstrong Heavy Lift Crane in Venice Dockyard and the manufacture of mills in Ethiopia. So over 50 years of experience there, which is reflected in his talks. Yesterday was the first on conservation of cast and wrought iron. The focus was on how cast and wrought iron traditional metals were smelted and shaped for practical use by the founder and blacksmith. Some of the many interesting and diverse uses of iron both in Great Britain and other countries were highlighted. So today we shall discuss the ethics governing the conservation of ironwork. We'll know the tips on surveying these structures, discuss both cold and hot repair processes, and he'll be illustrating them with case studies. Now, before I invite Jeff for the talk, again, I request all of you to please interrupt where you feel that something is not very clear. That's the way he wants it. So we can take a pause and we can discuss those points. So please do use the chat box facility to type in your questions. I'll interrupt the talk and we can discuss that point there, or you could do it after the talk. It's entirely up to you. Type in your name, organization name, and your email ID, please, in the chat box so we know who all has joined us. So I now request, please mute your microphones. It's a request because there's a lot of disturbance otherwise. And I now request Jeff to please carry on with the lecture. Thank you, Jeff. Over to you.
Okay, thank you very much for your introduction, Padma, and good afternoon, everybody. It's a great pleasure to be with you again. I'm sorry I can't actually be with you in person, but this is a good alternative, providing the line doesn't fail. So as Padma said, we at the last session dealt with the properties of iron, how iron is made and shaped, and how it's been used in traditional applications. Today I want to move on to much more practical things, how to actually repair this, but I want to start with a little bit of context. Here's a rather wonderful building that I had the privilege of restoring a few years ago. It's actually a plant house in a historic building. It comes from the early to mid 19th century, and it was on the point of collapse. You can see that there is a brick arch inside, and this was leaning somewhat and was about to collapse. And the reason it was allowed to get into that state, of course, was because it had become a useless building. It was allowed to get old because nobody wanted to keep plants in it anymore. In England, of course, in Britain, it's quite cold in the winter. And so unless you have a very effective heating system in these old buildings, they become useless after a while. And as fashions change and people wanted to grow exotic plants, no longer wish to, a building is no longer regarded as useful, and it therefore has no value. Now, I just want to plot that, if I may. This is a graph of usefulness or economic value. So I'm saying that a new building is constructed because it has to fulfill a purpose. Somebody pays a lot of money to construct a building, but it gradually starts to get old, it runs down, it might have a little bit of maintenance, and as it goes through its life, it probably runs down in terms of its usefulness. It becomes less valuable in monetary terms and may indeed eventually go into disuse. And then, of course, we get involved with it. This is where we're active in the conservation, the adaptation, the repair area. And it costs money. What we're doing costs money. So it then comes back up to the higher point on the graph. And we do that because it's going to be more useful. It might not be the same use as the original use of the building. And you may recall there were two photographs in that previous slide. The original building had become useless as a plant house, but it became useful as a wedding venue. So we've now got into the second phase of the life of the building. It gradually gets a little bit older. Hopefully there's some maintenance work done. Somebody's putting a little bit of investment in, but it gradually runs down again and may need to go through another cycle of adaptation, repair, conservation. I'm afraid this is life. It goes on and on and on like this. Now, I'm going to add another graph to this. This is risk. So the red line is risk to the building. Is this building at low risk, would you say, when it's new and valuable and useful? Would you agree that as it starts to get older and its usefulness gradually falls, the risk to it goes up? The risk of neglect and the theft of parts and so forth goes up. And that's at a maximum, I would suggest, when the building is disused. So when the building's usefulness and value is at its lowest, the risk to it is at its greatest. I hope you would accept that. But I'm now going to ask you a question. So could you be ready to respond on the chat very briefly and quickly? The question is, when we get into this area here, which is the conservation, repair and adaptation, is the risk to the building going to go up during that phase or down? So just respond briefly, if you would, on the chat, either up if you think the risk to the building is going to go up, or down if you think it's going to go down. Do we have any responses, Padma?
Yeah, we have about 10 and everybody's saying up.
It's going up.
Yes.
Aha. That's
everybody's saying an up. We are unanimous up.
Okay. So you think it's doing that? Well, that's somewhat of an indictment, isn't it, on our field of work? What we're saying is that when we get involved, it starts getting more dangerous for the building or the materials of the building. But I'm afraid you're absolutely right. Congratulations. The problem is, in metalwork conservation, in particular, we have some very powerful and potentially destructive techniques. We're using techniques that involve heating perhaps to several thousand degrees centigrade. We have cutting equipment that can reduce steel and cast iron and wrought iron to small sections in seconds. You're absolutely right. And so we have to be very careful in the conservation of these traditional metals to avoid doing more damage than we can. So would you accept then that the aims of conservation, particularly in metalwork, is to provide a new use or extend service life? So did you notice that on that graph, the area here is, the area is greater, the length of time for the second service life should be longer than the first service life if we do a good job. We're trying to extend the service life of the building or its materials. We're trying to render them durable and maintainable. And most importantly, from what we've just said, and what you've just voted, we're trying to keep the risks during repair and adaptation as low as possible, but we must also retain heritage value. So we've now introduced another word, 2 words. So let's see if we can define those. Well, Historic England have published a document which you can see there. It's available on the internet, and they say the heritage value is the sum of 4 values: evidential value, which is the potential for the fabric to yield actual evidence, and this is really the most important, the greatest value of any historic building or structure or materials. It's what they can tell us actually about the past. Secondly is historic value, which is the way in which the building provides a means of connecting people from the present to the past. There's the aesthetic values. Do people like it? And communal values, the meaning the building has for collective memory. Now, I can't develop this. You want to hear about the conservation of metal, but I wanted to set that context because it's very important in dealing with historic buildings. And you can, once you've got that framework, start actually ranking these different characteristics, the heritage value, the significance, if you like, of these different buildings. And that's quite important. So just very briefly read through those if you wish to, or as this will be recorded, have a look at it all later and have a think about those. But the point is you can start ranking the different characteristics and see whether they're actually important and how important, or intrusive. If you look down here, you can see that you need to also put in what is intrusive to help you make your decisions. Okay, so can I just summarize what I'm suggesting ethical conservation is? I think this probably applies widely, not just to historic metalwork, but we've been very keen in our business to make clear what we are selling as a service. So we're trying to do the minimal disturbance and loss of evidence. We're trying to retain as much of the existing material as possible. Often it's cheaper if you have a smashed casting to just cast a new one and it's stronger. But that's not actually what we think is conservation, ethical conservation. We're trying to repair and consolidate rather than renew. Again, that's usually not the cheapest option. We're trying to use reversible processes wherever we can. And I'm still trying to work out how to drill a reversible hole so that I can bolt on a plate. Just think about that. Holes tend not to be very reversible. It's good practice to add material to reinforce, strengthen, prop, tie. It might not look very good, but it's cheap, it's effective, and it doesn't disturb the original materials. If we have to use new materials, let's use traditional ones, traditional materials and techniques wherever possible, and make sure that what we do is distinguishable from the original, and to record everything before, during, and after our work. But I have to say, whether you will be able to find the records in 10, 20, 50 years' time, I rather doubt. And if you can, you probably won't be able to read them because technology tends to move on, as must I. I just wanted to mention this. I just mentioned it very briefly on Monday. Just jot down the website at the bottom there if you wish, www.nhig.org.uk, because they supply some quite interesting booklets. There's this one which deals with conservation ethics. They're quite cheap. And there's this one which deals with materials and techniques. And I just want to show you that one because last time I mentioned the different types of sparks that you get from by just grinding very gently onto a piece of historic metalwork. You can tell whether it's cast iron or wrought iron and possibly steel that way. So I just wanted you to
Jeff, if I interrupt, the covers of the book, we'll have to show them once you're off the share screen because right now, most of us can only see the screen.
Okay.
Yeah,
No problem.
We can show the books again.
Yep, I'll try and remember. Thank you very much, Padma.
I'll remind you. Yeah.
I'll move on. The other thing that came up last session was a question about distinguishing cast and wrought iron. So I've assembled this for you. Just very briefly, I'm going to run through. You can usually tell the difference between brittle cast iron and wrought iron, which is ductile, by its shape or design. So if something's been made from a wooden pattern, like a column or a panel or a beam, that's cast iron. Often you'll find cast irons used in compression and wrought iron in tension. And because you have to pour molten metal through a mold, cast iron is often in heavier sections than wrought iron. Now, do you remember we had to dress off a little leakage around the castings after they'd been cast in their two-part molds? Well, the mold line or the flashing, if you see that around the edge, that is cast iron. If it's a riveted construction, it's usually wrought iron. They didn't usually use rivets on cast iron because it's a brittle material and would break. If you have fire welds or forge welds, that's where it's just been heated up and bashed together. That's wrought iron. Might be steel, but usually wrought iron. If you can see tool marks in the surface, it's probably wrought iron because you're looking at what the blacksmith did to the surface. If you have blowholes or porosity in the surface, that's cast iron. I mentioned that if you cut a little tiny shaving off the edge, wrought iron will curl up, and cast iron, you can't get a shaving at all. It just chips. If you cut into the iron and bend it, you'll see that with wrought iron, you have a fibrous wood-like structure. With cast iron, you can't bend it at all. It just breaks. And I've mentioned also the option of putting a grinder against it or putting it against a grinder. If you get red sparks, it's cast iron. White sparks, it's wrought iron or possibly steel. Okay. So let's now look at some of the problems that we get in real buildings, real structures. I'm afraid life does all sorts of bad things to structures, like overloading. You often find metal structures used, perhaps metalwork used in bridges and the framing of buildings, and they just get overloaded or they settle and move around. Sometimes there are mechanical shocks. I'm not just thinking of earthquakes, but vehicle impacts and so on. Thermal shocks from fire, but also from past repairs. You often have original material and manufacturing defects, and they may well be on the inside, so that can be a worry. I've mentioned past design, alterations and repairs. Graphitization is something that you'll find in cast iron, and I'll mention that again in a minute. And I'm going to be talking on Friday a little bit about the corrosion process. So it's all about maintaining the metalwork if you can, dealing with the water, so keeping the joints sealed, keeping the paintwork in good condition, renewing defective putties on glazed structures, keeping the water managed properly, and clearing away biological growth, which holds the moisture. I mentioned graphitization. Now, any metal, any cast metal that has a high carbon content, like high carbon steel or cast iron, can suffer a rather rare but very destructive process called graphitization. It's a complex chemical process in which the ferrous matrix just disappears and you're left with graphite, which, as you know, like the lead in a pencil, is simply soft black. And you can see here, you've only got to tap a graphitized piece of cast or forged iron, and it will just disintegrate. It has no strength at all. We found that in places like old water wheels, where the castings have been perhaps buried in silt, or seaside structures where the footings, the piles have been buried in silt. Any anaerobic process tends to bring this on over a long period. So I just mentioned that because it can be very destructive.
Sorry, Jeff, we have a question. It says, what does a rub down mean?
What does?
A rub down. You mentioned occasional rub down. So they want to know, what does a rub down mean? The previous slide. Yeah, rub down and touch up. So they wanted to know what is rub down.
Oh, I'm sorry. That means taking an abrasive pad or some sand or emery cloth, something like that, and rubbing down to get rid of any protuberances, anything sticking up on the paint, or any rust. So rubbing down means to just rub away all the stuff that shouldn't be on the surface, and then touch in the paintwork, but you must get rid of the rust. I'll deal with this on Friday. So rubbing down to get rid of any imperfections, and then touching in the paintwork. Okay?
Thank you. Thank you.
So these are the things, these are sort of things we need to be looking out for before we actually start any work on a structure. You need to find out how it's put together and how it's intended to work originally, which may not be how it's working now. So originally, you need to find out which were the primary members, which were intended to carry the load-bearing the capability of the building, and then how the structure is working now. Remember, it may all have moved around, and things may not be vertical, things may have moved. That isn't a problem, provided the building has accommodated it. Just bear in mind that cast iron doesn't like to work in tension, it likes to work in compression. Wrought iron is happy to work in tension, but it's not quite so good in compression because of its fibrous structure. Then have a look at each element. Again, anything that is liable to be a problem for water. So footings, fastenings. Remember, you can't see the business part of a bolt or a rivet. It's actually inside, so you need to know what's going on inside potentially. Water traps, anything that carries water, thin castings, which are very brittle, of course. Anything that can hold water like crevices, splash zones, particularly at the bottom of buildings where the water splashes up. Interlocking parts, because different materials can attack iron. In fact, all the other metals, apart from aluminium and zinc, actually are aggressive to iron. So that's cathodic attack. I'm just going to show you some examples of where I've nearly got caught out in the past surveying iron structures. Here is a fireproof construction. It was actually an old army fort, fireproof construction with cast iron beams and brick arches. And I realized that the water was running down from the inside, but I couldn't see any damage. And eventually I noticed a little step at this point and realized what was happening. The water had caused rusting here. The rust expands. It can expand 5, 6, 7 times the size of the original metal. And it pushed down this, and cracks were developing from the inside. This is really dangerous. There's nothing holding this vault up. I must say I left that building quite quickly. You may recall the Iron Bridge, that wonderful bridge built in the 1770s. This is how it's held together, just like a piece of wood with dovetails. Water, of course, runs down here, rusts, expands, pushes that to the side, cracks develop where you can't see them, and the bridge could just collapse without any warning. And this did happen in the 18th century and early 19th century when they were relying on big castings in buildings and structures. They would just collapse without any warning. Whereas wrought iron, of course, does give some warning. It doesn't split like this. And if there's an overload or some problems, the building will accommodate it, it will move. Whereas with cast iron work, it will just collapse. And that's a real worry. This is a cast iron panel bolted to a frame. The condensation, perhaps in our cold, damp climate, runs down the back. Rust starts here, pushes that off, and without any warning, this fastening has nothing holding it. It's just doing nothing, and this can fall off. Now, columns inside buildings are almost always cast laying down. And if you lay a column down, if you're casting a column laying down, you have a sand mold, but of course, going up the middle of that mold is something to make the column hollow. It has to be what I call a sand sausage, running the full length. And when the metal is poured into this gap, the metal is heavier than the sand, and so it pushes the sand up. So you get a thin wall here. Now, supposing there's a bit of gas, maybe some steam comes off the damp sand, it's going to accumulate here. Supposing a little bit of silt or dross, as we call it, some slag goes in with the molten metal, that's going to float up here as well. So we've now got a weakness running along the full length of our column potentially. And often these columns are used in compression, sometimes used for water, carrying water. And if you are at a high altitude in India where it freezes and these columns are filled with water, the water freezes and expands, and of course it's going to split there. But if you've got a split there, you may well have little splits on the inside. So just be warned. You may see a split there, but there could be all sorts of other weaknesses around it. And remember, this was to be used in compression, this column. And so the one thing you really don't want is an eccentric load carrying capability like this. Moving on to wrought iron. I mentioned rivets, they can be broken inside and you don't know about it. The best way to find that out is to simply hit it. Yes, I'm a good mechanical engineer. I have a very good range of hammers, which I use extensively. You hit that, it'll just go thud. You hit that, it will actually ring. And that's broken because rust has built up in here. How do you get rid of that? Simply heat it up. You take an oxypropane or oxyacetylene torch, I'll illustrate one later, heat it up, the metal expands, the rust doesn't. And so they part and you just hammer it and the rust will fall out. If it doesn't, do it again. Don't, whatever you do, try and dismantle these things. And if you cut into one of these rivets, you'll end up probably spoiling the whole. I'll show you how to take a rivet out later. Another sheet of piece of wrought iron here. You'll sometimes find there are defects inside. If we were meeting in real life, I would show you some of these, but you need to know about these laminar defects. They're called ropes, and they can occur inside. One of the best ways of finding out whether your structure is strong enough and whether you have these internal defects is to simply test it. Put on a proof load, as it's called. Just pull it, push it, load it up in some way, and see whether it fails or whether these start to show themselves, whether they spread and split. Okay, so these are some of the options in increasing intervention, if you like. Can we just leave it alone? If we've got a new equilibrium, the fact that you may have wasted components or things out of alignment or settlement, it doesn't matter as long as they're not structurally significant. And that can apply to anything from a small scroll to an entire building. If it's structurally adequate, will do its job still, why not leave it alone? That's the cheapest option and the best conservation ethic. Can you start reducing the loads on it? Reduce the spans, perhaps, add some structure, put in additional beams? Could you change the stress regime? Cast iron doesn't like to be in tension. Can you put something in that keeps it in compression? Can you add plates or doublers? You can actually glue now with epoxy materials. You can glue on glass or carbon fiber, which can increase the strength hugely. And it's more or less reversible with difficulty, but it can be very effective. You could perhaps put resin inside columns to give them additional strength, although that's not reversible. If you have to, take the building apart. You can get a better understanding of how it's put together and what's the condition it's in, but you can do a great deal of damage, so do be careful. And you need to be mindful that there is a scrap value for dismantled metalwork, so just beware, you have to keep it secure. You can more effectively paint all around everything if you take it apart, and you can renew those fastenings. You know what you've got in the way of integrity there, and you should be trying to do it in the reverse order to the original order of construction. And again, careful recording at all stages. I'm sorry to rush so much through this, but it's rather a big subject. Let's rush on now to hot repair techniques. If you're going to use a hot repair technique, you need some form of energy. And nowadays there are basically two forms. One is electric arc, which means basically you have a transformer and you short together the output. It's great fun. You get a great big spark, which is a plasma. It's about 6,000 degrees centigrade, and it will create a weld pool. It will melt locally the metal, and the weld pool, as it's called, will be about 3,000 degrees centigrade. So that will fuse the metal together. It's called electric arc welding. MIG is metal inert gas, tungsten inert gas, or stick welding. But this is not great news for castings, because being brittle, castings will be shocked and usually the weld will fail. You can weld cast iron, but it's not recommended. It's okay on wrought iron. It's all right on a site, except that, of course, historic sites don't like we don't like the risk of hot work on historic sites. So if we're worried about heating something to such a very high temperature and so quickly, why not instead use gas? Propane or acetylene used with oxygen. It will heat to about 900 degrees centigrade, but much more slowly. So that is okay for cast iron. You can heat up slowly, and it's okay for wrought iron, but of course on site, we really, again, don't want to have these hot works, and this is a very hot naked flame. So that's not a great idea on a site. I mentioned hot work on castings. You can preheat cast iron and then arc weld with often nowadays nickel rods, but I personally, in my consultancy, only ever recommend this for non-structural applications. This is fire welding, where you heat up the two ends of wrought iron, only for wrought iron. You can do it with steel, but not cast iron. You heat up both ends white hot and hammer them together. Here, this could be a cold repair. In fact, you could simply fill that hole with a resin. If it's more extensive damage, this is gas welding on wrought iron. And here we've got brazing, that is using bronze as a filler. So you can see that it is, future generations can see that it is a repair. It's non-corrosive, and it can be done at about 900 degrees centigrade, or even lower if you use a different mix. And so it's much less dangerous for the metal itself, for the parent metal itself. That's a good way of carrying out localized repairs. And if you have a damaged section like this, no need to replace the whole thing. Just cut where it's sound, take out the defective part and put in a new section. And that can be, in this case, either gas or electric welded together. So if hot repair techniques are no good or not preferred for castings, can we use cold repair techniques? Well, do you remember how much carbon there is in cast iron? Those of you who were with us on Monday, you may remember it's about 4% of carbon. Carbon is a very good dry lubricant, so it's easy to drill castings. So why not just drill in and bolt the pieces back together, bed them on some epoxy putty or something similar, or put a plate across the back and bolt them in. Remember, of course, as you're drilling holes, you are actually weakening the metal again, so keep the holes back away from the fracture. If you can't get to the far side, it may be something like a circular baluster. Maybe you can hide the fastening inside, so you can drill and tap or thread both parts and screw them together, bedded on an epoxy again. If you can't screw these together, what about drilling and threading into one side and just gluing it with an epoxy putty into the other side, like this? So there are various ways of simply inventing a mechanical fastening which can be done cold, and they're very effective, including the adhesive types nowadays. I mentioned the longitudinal cracks in columns. I'm afraid this is relatively common. Can you see the crack running right the way up through this rainwater pipe? Indeed, there's a crack there as well, running all the way around. And you may be able to see some little stitches. And this is, again, the crack. This is the stitching process. So here is the crack running across, and we've taken a jig and we're drilling some holes across. These holes just interlock like that, but you just clear each other. And you then take a chisel and chisel the little webs between the holes, and you knock in a thing called a stitch. It's a sort of wiggly piece of metal like this. It's a ferrous material, and you can knock them in, stack them up, make them almost to the full depth of the casting if it's quite thick. Now that will stop the two parts of the casting from moving up and down, as it were, and apart. I'm sorry, it'll stop them moving apart, but it won't stop them moving up and down. So now we drill along the line of the crack, interlocking holes, and we screw in some metal studs. Screw them right down, and then dress them off, and put a coat of paint on, and you can't see where you've been. So now we have a metallic fixing, a stitching with the crack infilled with studs. So this hasn't used any heater tool, they're just hand tools. We've done this over a river at night to avoid disrupting river traffic on a bridge. It's a very effective process. It can return almost 100% of the original strength. But remember again, drilling all these holes does locally make it not so strong. So a very good process. It's called stitching. There's a process called metallock. That's a patented process. You have that in India, so you can use metallock for stitching historic castings if you wish. Do you remember that from last week? This was the client was moving this two castings, parts of a locomotive turntable off a railway. They were going to a museum. And I'm afraid the haulage contractor didn't realize just how heavy and slippery castings are. So this is one of my favorite photographs. And fortunately, they kept the bits. The important part, if you do have a serious accident like this, is to make sure that nobody steals parts as souvenirs or something. Often cast iron breaks cleanly. And so as you can see, it is possible to put it all back together. And can you see the little stitches there, just beside the strap? So we're clamping this up and we're about to stitch it, the process I showed you previously. And you can have stitches, you can pile them up as much as you like, and you can put them in the side. So it's a very effective process. You'd never really be able to heat this properly anyway, so cold repair is the only way of doing it. And once you've put in the stitches, so here is the crack, here are the stitches, and along the line of the crack are the studs. And once they're dressed down and cleaned off on the surface, you can't see where the repair is. It's very effective. If you were to pull this apart, this would actually break from the end of a stitch here to the edge. So that's where it's vulnerable. And from there to the edge there. But I'm getting a bit technical now, I better rush on. Okay, let me show you a few case studies. This is a lovely cast iron parapet on a bridge near where I live.
Jeff,
Yes?
we have a question.
Yep.
Question is, can't we drill a fine hole across the crack and pour some same molten material in it to hold the crack?
If you drill a hole at the end of the crack, that reduces the stress raising characteristic of the crack. It tends to stop the crack propagating, but it won't strengthen it. Usually the cracks are very fine, unless they've completely broken apart. If the crack is just a fine crack, you can't get anything into it to fill it. If you use an epoxy or something like that on this situation, here, you'll find that it's not strong enough. It will fix it back together, but you wouldn't be able to get sufficient strength in just 1, 2, 3, 4 points to withstand the sort of heavy loads that this has to put up with. So the answer to your question is yes, you can certainly put it back together with adhesive. In this situation, you would also put plates on the side. You would glue plates on the side here, but the client here wanted a repair that he couldn't see, and also because other things have to be mounted on the top of this, we couldn't put a plate on because it would cause an obstruction. So there is no correct way of doing these repairs. What I'm showing you is a lot of different options, and you can choose from them. And the option that you've just suggested is one of them, but in this case would be limited to limited because of the lack of strength. Okay?
Yeah, thank you.
Any other questions? That was a very good question. Thank you.
No questions now. I think we can move on.
Okay. I had a visit from the bridge inspection engineer who told me about this bridge and said that this is made of grey cast iron, which, as you know, is very brittle, and it doesn't any longer comply with the latest legislation for controlling vehicles. So if a vehicle, a lorry perhaps hit this, being brittle, it would break, and there's a river underneath this, and so it'd be very dangerous. And he said, could you replace this with a higher grade of iron? Now, you may recall at last lecture, I said, yes, we can. We can use, can you remember what it was called? Spheroidal graphite iron, which is ductile and malleable, and lorries will bounce off it. But I said, what's wrong with the existing one? To which he replied, nothing. I said, well, we're certainly not going to scrap it then. Why don't you simply build a fender along the side of the road and bounce the lorries back into the oncoming traffic? Well, you can't do that. That's not good highways practice. And I said, no, but it's good conservation practice. It would protect the historic material. It would give somewhere safe for the pedestrians to walk. It's cheap, and it would be effective. And that's exactly what they did. Now, if you actually drive along this road, you see that there's a great big fender there, and so you slow down naturally. Actually, it turned out to be very good highways practice as well. But I'm showing you this example because the best form of conservation is to make the problem go away. We had said, basically, yes, we can do it, but we're not going to, because we think that it would be wrong to throw away this perfectly good historic structure. And by saying that, they realized that actually that wasn't the best way forward. The best conservation option was to make the problem go away, just protect the old metalwork and move the problem elsewhere. Here's another example, another bridge near my home, in my home city, in fact. This is a wrought iron structure with cast iron plinth and cappings. And the same problem, it had to be upgraded to keep vehicles from driving into the river here. Now, fortunately, we have these lovely backstays. So we dismantled everything except the backstays. And then we put steel posts in and welded them to the backstays. Here we are, a weld steel post. And then between the posts, we put another steel rail running right along, welded that on, and then put the original material in again, which was simply cosmetic. The strength is in the new post, the new rail, and the backstay. So that now becomes a clear modern structure made of modern materials, if you like, which is determinate. Structural engineer can calculate the strength of it, and all the original material becomes redundant. The handrail was machined away to cover that top rail, and everything else was put back exactly as we found it. Notice the different colors. That's because we do the surface preparation and painting in the workshop, and when we bring it back on site, of course, we do fitting and drilling, and that spoils the paint. So these colors have to be different, so we can build up the different layers of paint we can see that we have all the layers on there to provide the necessary specification. More about that on Friday. Now, this is a wrought iron gate in a very posh house in the south of England. And it doesn't look very good, does it? But is it structurally adequate? Well, the primary frame is good. The secondary structure is just about structurally adequate. Might need to put a bit of metal in there, but otherwise it's all right. It's actually only the decorative work that is not very good. Well, actually, that one's all right. That one's all right. We're not too worried about the corrosion. This has lost the end, and that one's nearly gone as well. So actually all we really need to do, minimal intrusion, is make a new scroll, put a new end on there, do some flame cleaning to get rid of the rust, and put a jolly good coat of paint on it. Now, I was giving this lecture some years ago, and a gentleman at the back of the lecture theatre said, "Why are you doing all that? That's not minimal intrusion. Minimal intrusion would be to get rid of the rust, just secure that back onto there, then clean it all up and put some paint on." But then an argument developed because others were saying, yes, but originally it should have had all its scrolls. It's clear that that's what the blacksmith intended, and we're restoring something to a known earlier condition, so that's valid. And then somebody else said, yes, but what does the client think? The client's not going to want half a scroll there. He's going to want the whole lot made to look beautiful, especially a rich client, and this is in his garden, it's near his house. And then somebody else said, well, yes, but if you think about the ethic, you wouldn't be putting the arms back on the Venus de Milo, would you? So why are you putting the ends back on your scrolls? And this degenerated into a sort of argument about conservation. Now, I'd love to have this discussion with you now, but we don't have time. But the problem, of course, is that there is no single best answer here. What we have is a series of principles, like minimal intrusion, using traditional materials, trying to create the longest durability that we possibly can, and so on. And some of them are incompatible. My question is, do you think, therefore, these principles are invalid? Is there any point in having principles if we can't actually apply them? Don't answer that. I think the answer is the reason that we have the conservation principles is because if we don't have any rational point to start our discussions. We know that we're trying to do nothing to this. Ideally, we'd like to leave it alone, but we can't do that because it won't survive. Therefore, the next step is we have to put a coat of paint on it. So that's minimal intrusion, but that may not be satisfactory from the client's point of view and various other points of view, structural strength and so on. So we now have to do a little bit of repair work, and we're getting pushed all the time into a little bit more intervention. But that's a rational process and one that we're quite happy to do, provided we know where we start from and the implications of all our steps. I hope you accept that, and I'm sorry we can't have a discussion about it, but I run a course in Sussex in Westdean College, so if you'd like to sign on to that course, come and see me then and we'll continue this discussion. Shouldn't say that, should I? It's advertising. This is a wrought iron window frame at a historic house in the south of England. Actually, there's nothing wrong with it apart from this bottom sill where the water has been ponding and splashing. The problem here is getting the glass out. It's very difficult to get glass out of this situation, but by scraping and getting rid of the putty and gradually agitating the glass, get it to debond, it is possible to get the glass out. Then we can cut there and down here somewhere, take out the bottom piece, straighten up this, forge up or machine up a new piece of recycled wrought iron to put in here, make this glazing bar section, and weld that back in together with the original subframe here, and then put the original glass back in with a little repair in the corner. So yes, there's a lot of work, but that's what we're trying to do, retain all the original material, including the glass. This is a bridge in North London after it had been overloaded, collapsed into the river, been washed downstream, pulled out behind a tractor, and then put into the council's depot for safekeeping. And it's made of wrought iron. So our task was to make it into one of those. Now, if you take off the balustrading from this point up, you're left with the structure. It's called a lenticular truss, a lens type truss. And it has one compression member and one tension member with braces each side, and that's all there is. The reason this failed was because these two lenticular trusses relied for their stability on transverse bracing, which was initially provided simply by the wooden deck here, and when that rotted, it collapsed. So when we put it back, we put in some diagonal metal bracing to give it strength. But you can appreciate that this is a very economic structure. It's nearly 100 years old. There's corrosion and so forth. So how can we be sure that this is strong enough when we finished, especially when you start with a lot of junk like that? Well, we knew it would be easy to straighten these things because it must be good quality wrought iron for to have survived on a structure of such delicacy and such a large span. So we can straighten the components, but the only way then of telling whether the final result is strong enough is to do a proof load test on it. So what we did was erect the lenticular truss without its balustrading in the workshop and put a proof load, a test load in the middle. We just pulled it down with a chain hoist and a load cell to the equivalent of the pedestrian load that it was designed to carry. That was supervised by a structural engineer, and of course it passed its test. It went back up after a test to more or less where it started and had proved all the repairs that we had done, the fastenings and so forth. So that's how we can prove the strength of these historic structures that may have original material defects in them. And indeed, we may introduce further stresses and defects and so forth. It can all be tested by putting on proof load. This is a late 18th century tomb. Fortunately, the conservation officer had been collecting these because the children were using them as weapons, but he was hiding them away on site. So we simply had to put it all back together using the original stonework. Now, this is wrought iron, 200 years old, and it hasn't been painted much in its life. It's only failed in the splash zone or where the vegetation has been holding moisture. So that's why it's so important to keep vegetation and algae growth off metalwork. Wrought iron actually has a black coating on it. It's called forge scale, and as it comes from the original forging process, remember our talk on Monday, the forging and hammering produces this oxide layer. If it stays intact, it will protect the metal very well, but it tends to fall off, particularly where there's persistent water. So nothing wrong with these railings apart from just the ends. So we chopped off the defective ends and fire welded on new pieces of recycled wrought iron. And here we're using an epoxy paint because when we come to lead these back in, the lead will try to burn off the paint, but epoxy paints will actually survive molten lead. It's very important to use this traditional fixing if that was there previously. So the lead is poured in round the paling, but it must overfill the hole so that you then dress it down so that it's nice and watertight. Otherwise, there's a little bit of a gap where the lead contracts away from the metal. Okay, important not to just use resin where we have these traditional fastenings. the lovely little lead rosettes at the intersections of these crossing items here, some of those were missing. So we made up plaster of Paris, molds to clip on here. They were just put plaster of Paris on each side and then divided it and took the two halves apart, clamped it onto the next one here, and then poured in lead, then dressed off all the defects, as you can see, to make a little replica. There are various mold materials you can use. Nowadays you can use something called ceratite, and there are various other molding materials that you just put on with a bond breaker between them, so that you can take the two halves apart, and then you can pour in lead. You can see where it was poured in the top here. The surfaces were not dressed in any way. There's very rusted surfaces. There's nothing wrong with a rusty surface as long as it's thoroughly cleaned before you put the paint on. The Royal Botanic Gardens in London, in Kew Gardens. This is a plant house that was built for the Amazonica lily, the giant lily, which needs very warm water. So it had this heating pipe in it, but that of course produced a lot of steam. And that rusted the roof of this building, which was put up in the 1870s. And so I'm afraid the props went in, and our task was to take the roof down and repair these defective trusses. It all came apart beautifully, so bear in mind that often these traditional structures will come apart really very easily, but it's very important not to do any damage whilst the components are being lifted by crane. Now the problem is that the crane driver can't actually feel the lift. He doesn't know whether he's applying 1 ton or 20 tons. So the whole operation must be controlled by what's called a banksman, a conservator who knows how to get these joints separated without doing damage. That's really important because you can destroy cast or wrought iron structure by leaving it to somebody who doesn't really know the metal the capabilities of the metalwork. The problem here was that these bulbous T's had been repaired and the repair plate hadn't been sealed properly. So nothing wrong with this 100-year-old material here. It's just where the water had got underneath the repair plate. So we turned these trusses on their backs, cut off the defective plate, and welded on some recycled wrought iron with, of course, the grain running in the right direction. Very important. And you can see 2 men, one each side, welding at the same time. They're doing this because welds contract and the whole thing will bend if you don't keep it balanced. Now, the problem is that we have a wrought iron with a longitudinal grain and a repair plate with a longitudinal grain, and the contractions of the weld tend to pull the grain apart. So you end up with tiny cracks. Here we are, we've laid down this truss now. There's the repair plate, there's the original T-section, and there is our weld running along the truss. And the cracks develop along the side of the weld or through the weld. So here we're doing a magnetic particle test. We've cleaned this and then sprayed on a magnetic ink, which has little tiny metal particles in it. And those get down into the crack. So you then clean off the surface, put on a developer, a white powder, bring along a magnet, and if there's a crack, you can see very clearly where the ink is coming out. It's a very good process. There are various other types called magnetic, other sorts of dye penetrant techniques. But again, what we're doing here is testing the repairs and the original material to see whether they're fit for their purpose. And this is another way of assuring ourselves of the structural integrity of the original and repaired material. So it's all perfectly doable as long as you know the different techniques that you can apply for the repairs, the advantages and disadvantages, and the checks that you can subsequently do, and the tests, the proof load tests, if those are necessary. Now, just finally, as we're getting towards the end of our time, want to show you where the roof was repaired here. This, again, is the Water Lily house in Kew Gardens that I just shown, but the roof glazing bars, in many cases, were too far gone, too far rusted to use. So the specification at the time was to use stainless steel. Now, there is a problem with stainless steel. It has a lot of nickel in it, and nickel is aggressive to iron, to wrought iron and cast iron and steel. And if you put them together in a wet environment, like a plant house, then the stainless steel, whether it be in glazing bars or in bolts, will attack the iron. The best thing is to not use stainless steel. Nowadays, we would forge wrought iron or even roll wrought iron to the right section. And there is a company with which I'm associated that rolls these sections in wrought iron nowadays, recycled wrought iron. But the reason that you shouldn't use stainless steel is because if you look at the galvanic potential in millivolts between, for example, iron or steel or cast iron up here, that's about 600 millivolts in relation to the nickel chrome alloys, which are 0. So that you can see that between stainless steel here and the ferrous materials up here, there is 500-600 millivolts. That's half a volt. That is a very significant potential. And so the corrosion between the ferrous material and stainless steel bolts or any other parts, any other sections of stainless steel can be very high. Now, Padma, I can continue, but would it be a good idea to invite questions on what I've said so far?
Yeah, I'll just type in. There are no questions so far. There was one from Anuradha. She wanted to know the kind of rust inhibitors that you would recommend for Delhi's climate. A question on rusting, rust inhibitors that you would recommend for Delhi's climate.
For Delhi's climate?
Yeah, rust inhibitors.
Okay, I'm going to deal with corrosion and surface coatings on Friday. But when you say a rust inhibitor, there are various rust inhibitors like rust converter and different sorts of modern preparation that you can put on. If you're not painting, these inhibitors really don't work very well out of doors. If the metalwork can dry very quickly, and I know that in your climate you get very heavy rain, but also it can dry up very quickly, you may well find that it doesn't rust very quickly, and that an inhibitor like a rust converter or perhaps something like linseed oil or one of the other single pack coatings might be effective. Otherwise, you would need to paint. And if you could make time available on Friday afternoon, I'll give you the details there of the paint coatings.
Any other questions?
Okay.
No. Okay.
Would you like me to continue for another 5 minutes?
I think let's finish we can continue and finish it. I think we have about 15 odd minutes.
15 minutes?
Yeah.
I don't want to outstay my welcome, Padma.
No, I think you can continue. There are no questions at this point.
Okay. Well, this is another example of repairs to that structure. Stainless steel plates and bolts. Very important to either not use them or to separate them. So the plate here is set on a neoprene gasket. This is on the gasket. These have little cylinders of PVC around them. So if you are going to use stainless steel, which I don't advise, then you must physically and electrically isolate them. Toughened glass, 3mm toughened glass going back into this historic structure. Now, here is an area of cast iron. They're basically C-shaped, and there's a gap behind them which will never get painted in the future. So here, after the castings had been painted and re-erected, they were filled with a closed cell foam. Really important that it's closed cell so that it doesn't absorb water. And you mustn't put in something like concrete, because if the water does get down the back, it will cause rusting, and the rust expands and will break the casting. So a closed cell or some other compressible material if you must fill gaps. Isn't that a lovely structure? Very economic wrought iron roof structure. Riveting is a very good way of joining wrought iron together and steel together. A very quick process. And to extract the rivets, it's best to use something like this, which shears off the heads. So it's a long chisel, it's a pneumatic chisel, if you like, with a bit at the end, which is about 40 millimeters wide, 1.5 inches wide, and that's put under the head of the rivet. And this gentleman here fires a shot, a bullet, if you like, down here, which hits the end of the chisel and shears off the head. That's very quick and can remove a large number of rivets, provided it's a strong structure. Obviously, you can't do that on delicate structure. If you try drilling into rivets, you usually start damaging the original material. But this technique is quite effective as long as it's used carefully. Now, I showed this cathedral, Salisbury Cathedral, last session. And this is the bond that I was telling you that goes all around the outside. It was made in the 14th century, and it's had a brittle failure here. This is now no longer working structurally because obviously some later wrought iron has been put in. But the repair to this was to simply cut a little piece off there and weld in some modern steel, not attempting to disguise the fact that this is a modern intrusion on a historic structure. For cleaning, this is a good way of doing getting rid of the majority of metal, paint on a historic structure in an exposed environment. So this was up a scaffolding. I think I won't say too much more about this because on Friday I'll be dealing with this technique. It's called a needle gun, and it's really very effective. Whereas blast cleaning, which is even more effective, has all sorts of problems. You can't really see what you're doing. So that's, come back on Friday and we'll unpack this problem and the solutions to it. This is talking just a little bit about protecting a very exposed environment. You must have the right thickness of paint on, and you can, of course, protect by putting some other material over the top, like lead. And then you have to be very careful to seal along here, otherwise you've made it worse, because any water that gets in here will now be trapped. So if you are going to protect metal with another metal, you must be sure that you're not making the situation worse. This is a rather wonderful fountain by that famous Coalbrookdale company that made the big bridge in Shropshire. And it's made of cast iron, and the wings, for example, are made of two pieces joined together. Look at that. They're very thin, delicate castings, absolutely beautiful. And there are little feathers. You can see the feathers on this. This is a swan, a boy riding a swan. And unfortunately, the head had broken off. Now, this is what happens if you repair a casting with hot techniques. This is actually an arc weld. And of course, it's been welded here, but you can't preserve the detail. So this is one reason for not doing a hot repair on a casting. Afterwards, we had to actually chisel in and cut in all these little feather marks. So if you can avoid using a hot repair, it's best to do so. Here is another cold repair. This is actually the body of the swan, and always these are made hollow, these castings. It's cracked, but we've just put a little stitch here, and we're now strengthening the whole area by putting a cast iron pad. We've made a new cast iron pad from a wooden pattern, and we're going to put that inside, bed it in with an epoxy, and then bolt on here through the holes, the wings that were on the original. And I just end up just to point out that there's always a comedian on the site. We have a great deal of fun with our metal conservation. We try and keep the staff really engaged in it and talk to them about all the ethics of what they're trying to do so that they make the right decisions. What we're looking for actually is not creative people, but ethical people, people who will work to the rules that we've set as we set out at the beginning of this, this lecture. And I'm glad to say that over the years, we've assembled a team that are really very reliable in doing this. And I think the greatest asset that we have is the people who we can rely on to do ethical work, particularly if they have a sense of humor. Okay, thank you very much for watching, folks, and for being so tolerant.
Thank you, Jeff. Thank you very much. Today was a very interesting lecture. Any questions? I don't see any questions typed in. There was a small request. Those books that you had mentioned,
okay,
just tell the names, I'll type them in, or if you could type them in. Yeah.
I'm going to stop sharing now.
Yeah.
Okay, Padma?
Thank you.
Okay. The first one is called Conservation Principles with Illustrated Guidelines. Conservation Principles with Illustrated Guidelines from nhig.org.uk. And
sorry, I didn't get that. nhig.org.
.org.uk,
Okay.
yeah.
Okay.
And it deals with all sorts of ethical issues. There are 15 guidelines set out in there and practical guidance about how to carry out restoration work. Then the other book is called Materials and Techniques for Forged Ironwork. So this is dealing with forging.
Okay. Okay.
And this one has various techniques that are mentioned in there, different materials. You may remember that last time I said that you can tell from the sparks what the different materials are sometimes. I'm afraid this is not reproducing very well, but you can see there some photographs of the different types of sparks. So you can see at the bottom there the sort of ragged sparks that you get from wrought iron. Okay, so this is a sort of practical information that you'll find in this booklet. They retail at £10 in England, and I think you can get them on the website. If there's any difficulty, let me know. Okay.
Any questions? I don't think there are any questions. Thank you very much, Jeff. Small thing, I wanted to extend a thank you to Barbara, Dr. Barbara Beckett. I forgot to mention her last time, and everybody should know she's been the one who's helped us in coordinating this lecture series. So thank you, Barbara, if you're there. So I forgot last time. Apologies for that. So everyone, thank you so much for joining us today. So the third lecture is on Friday, 4 o'clock. So we'll see you then, Jeff. Thank you very much for your patience.
Okay, thank you all. Thank you very much. Have a good week.
Yeah, you too. Bye.